Yes. All right. Welcome back. Our second speaker is Andrzej Weber from University of Warsaw. The title is Elliptic Classes of Link Pattern.
Thank you. So I should say that this work somehow is a combination of different influences. One is from Richard when we work about elliptic classes of Schubert varieties. And other direction was done with my student Piotr Rudnicki. It was about motivic chain classes that would Jörg present later. This motivic chain classes for something that's appear in a moment. The nilpotent two orbits of the Borel group acting on matrices. And also there is a big part of work with Jakub Kącki, but this is somehow the general outcome, the summary of all these different directions. So basically, okay, I will talk about group. In general, it can be semi-simple, but my favorite semi-simple group is GLN. Yeah, which you, of course, this center you can neglect, but let it be GLN and Borel. But by the way, is it visible from the back? So Borel group is the upper triangular. And the Schubert varieties, you take G over B, Schubert varieties in a plug, and you act with the Borel group, and you look at the orbits and then take its closures. So you have open cells, you have closed Schubert varieties, and all the calculus, Schubert calculus is here. Also, the calculus of characteristic classes is in this space. In the usual cohomology, in equivariant cohomology, you can move to K-theory and to elliptic theory. But I don't want to introduce elliptic theory. And all this calculus can be, in fact, moved upstairs. So here you have endomorphism of Cn, and this is a quotient. This is a non-reductive quotient, which is the subject that is present here. And in fact, my idea is that move all the calculus here and perform it there. So, for example, for cohomology, you have cohomology of endomorphisms of Cn, but with respect to a here Borel group is acting on one side and divide by on the other hand, on the other side. But upstairs there are two Borel groups. I mean, one from the left, one from the right. But if you look at the cohomology, it's enough to look at the tori. And there is a surjection to cohomology, equivariant cohomology with respect to torus of G over B. So this is a very basic example of a Kirwan surjective. So instead of tracing what's happening in the what happens for the Schubert varieties, I look for the B times B orbits in endomorphism of Cn. So you have orbits which represent the non-degenerated matrices. They go down here, and Schubert calculus is based on that. But also you have generate matrices, which lie on the boundary. And everything is parameterized by a combinatorics. Here, this is not really algebraic geometry, it's a combinatorics. You know by Brouwer decomposition that every double coset of B times B contains one permutation matrix. So I will just do it by some reason by something like this. So this is permutation matrix from 1 to n. And if you go to the closure, some entries can be omitted. Because there is a generalization of the Brouillard decomposition that every matrix up to double action of Borel can be represented by matrix that has only zeros and ones and corresponds to some partial permutation. And I go further. I just join this. So here you have x1, xn, and then other variables, but I will call them x1 plus 1, x2n. And now I consider linking patterns. That means something like this, and maybe also this. So there will be oriented linking patterns. And I also allow arrows like that. Maybe I will not give a precise definition. This is just to not every nodes play the game. I mean, there are some loose nodes, and there are arrows that one node has can go only from one node, and I mean, these arrows cannot have the common beginnings, common sources and targets. So this is combinatorics, and this parameterizes two nilpotent orbits. Orbits in, so if I take 2n, so this would be in endomorphism of Cn. So if you have matrix, just a matrix of n times n, you can associate a block matrix A, which would be necessarily two nilpotent. So in fact, I just concentrate now on these two nilpotent matrices, and I want to compute characteristic classes. So characteristic classes, I take, so just let's say n, which previously was 2n, and I act with Borel of n-dimensional, acting by conjugation on endomorphism on Cn, and I take a closures of orbits. So you have orbits, orbit closures. So these are my objects. In general, they are singular manifold, and I want to compute the characteristic classes. So you will hear many characteristic classes maybe in future, but let's start for the beginning with the simplest one, like the fundamental class. So there is something like a minimal orbit. Let's take m equal 4, and the rank of the matrix it's called somehow, okay, minimal orbit of matrices satisfying square 0, and so minimal rank of let's take 2, and then okay, and it will be this block. You take 1, 1. So this is matrix which square 0, satisfying that square is 0, and it's the orbit of the Borel group of the minimal rank, and its orbit is something like this. Here, the element which is non-equal 0. Here, element non-equal 0. This is whatever. So this is described by the linking pattern of this form. So you have third vector goes to first. Maybe look at this. Third vector goes to first, and the fourth vector goes to second. So this is like this. And the characteristic class, I look at the equivariant characteristic class in all the space, but with respect to group acting. The group is acting the torus, acting by conjugation, and also you have radial action. So this is easy. This is a vector space, and in fact, if you look at the orbit, so this is also easy because this is a vector space, but divisor just given by non-vanishing of this term. So the formula is easy. Maybe I would not write formula because it depends on what you want to study. If you study fundamental classes, this would be just the product of the zeros, the weights of these zeros. Or if you work on, say, Chern-Schwarz-McPherson classes, to be more sophisticated, you have to multiply also by some items coming from the other. But let's not talk about formulas. It's important that on this is acting a symmetry group. So what can you do? You can, for example, change this arrows. Just conjugate with the first transposition of the first two coordinates. And this would be the same as the following link pattern. And also you can make a other transposition. And then you would get basically the same, but you see, this would be inner. But further, I moved to Borisov and Weber elliptic classes, and their definition, there is a boundary data important. So the boundary divisor have labels. So there are variables. You have, so here, for example, you have variables alpha, and here variable beta. So if you transpose here, so then beta is upstairs and alpha is inside. Okay, so here would be the converse, alpha and beta. So as the orbit, it's the same, but there are different data on the boundary. What's my time? 7 minutes. Okay, so maybe I leave it like this. And then I'll move to the calculus. So the calculus is based on the elliptic functions. So Hirzebruch defined elliptic genus using certain power series. So first take a theta function. This is in fact Jacobi theta function. I will not write down the formula for this, but this is the most obvious function that you ever meet in the nature. You take elliptic curve, and you have to point a divisor on an elliptic curve. What is except the empty divisor? There's only one that comes to mind, is just 0, or the neutral element. So theta function is a section of the line bundle given by this divisor. And that's it, up to a scalar, but this scalar would cancel out in my formulas. So theta x. So this is a section of some bundle of an elliptic curve. And these line bundles are classified up to a shift by a quadratic form. So this bundle is a section, this bundle has a type I use 1/2 convention, 1/2 square. So every bundle on a product of elliptic curve is associated to a quadratic form. This particular case is just one elliptic curve, and the quadratic form is 1/2 x squared. And then I will use delta function xy. So this is theta x plus y, theta x, theta y, and so this does not depend on the normalization. So here yes. So what is the type of this function? So this is x plus y squared, 1/2. And if you divide, you subtract, because you, like a tensoring with the inverse of the bundle. So we subtract x squared, y squared. And this function was already considered by Don Zagier, and Liebgober has a nice paper about it. So it plays a building blocks. As a building, it's a building block of our theory. So the idea is to define operators. Aha, and I should say, I can think about this theta function as a section of a line bundle, but if I take a cover of the elliptic curve or the product of elliptic curves by a affine space, then I get just function, in this case a meromorphic function, with certain transition properties. And these transition properties are encoded in the formula, by the quadratic form. So we define operators, so Ci, depending on a parameter, on functions, which is like a divided difference operation, divided difference operators. So maybe I said that I call this variables xi, and here mu f plus delta xi plus 1 h. H is an arbitrary variable present in this theory. So this these operations satisfy braid relations. That means Ci mu composed with Ci plus 1, and here mu, say ni. Maybe I use additive notations like this. Aha, so I use this multiplicative notation, but this is maybe it should be additive when I, yeah, this is.
And you need an F.
Yes, and then SIF, transposition of F. Like a divided difference operator, you take F and F with transposed, and both parts are multiplied by something. And you have braid relation, Ci mu, this is the same, Ci plus 1 mu, C mu plus ni, I C mu I plus 1. So maybe I should explain from where it comes, because our thing is somehow related to braids. So if you have A, B, and C, now strings have labels. So if you cross here, just take A over B. This will be our new in the definition. Here crosses A times C, and here crosses C B over C. And this is the same as my time is done.
Why don't you just finish in a minute or so?
Okay, so A, B, C. So it would be B over C. This is A over B, and this is A over C. Okay, so this great relation for the elliptic, for this elliptic operators are can be illustrated by this picture. And the outcome is the statement that these operations compute elliptic classes in the sense of Borisov-Liebgober for certain choice of boundary divisor. And this boundary divisor is somehow determined by the fact that you want to stay just in one line bundle. If you change this boundary divisor, all would fall out into pieces. These operations having F, which is line bundle section, if you use wrong mu, then this part would be of different types and it would not make sense. So anyway, this purity of elliptic classes impose the condition that you impose the condition on mu, and using this operation you compute elliptic classes, which I will not define because in 20 minutes it's not possible. But this is generalization of the fundamental class, basically far-reaching. So 1 minute overtime.
That's okay. Thank you. Next question. It's possible to do it in a few seconds. Do you write down the square of a CI operation so that we can put it in a hack algebra?
Yes, we know the square. I mean, but in my notation, the square makes sense only if you have mu, and here mu minus mu. And then it's h mu inverse. So here is an additive notation, here is as you are. And this is what appears in our yeah. And if you really want, you can normalize this and have square equal 1, but maybe it's not necessary.
Thank you. Any other questions? Yes, and the speaker again.